in this episode.
Can't tell you how many times we sat around a table and said they want us to do what?
I think we still have to pinch ourselves when we look at this building.
The world's most slender skyscraper.
No one has ever put together a project as unique and as special as this.
And the pioneering historic innovations.
It's deflecting quite a bit. We have to find another way to make it stiffer against the lateral force of the wind.
I can't even imagine how windy it could be here in a storm. The forces must be just enormous.
That made the impossible possible. New York City is the most densely populated city in the United States. The iconic island of Manhattan draws millions from around the globe to live, work, and play, and its real estate is among the most expensive in the world. Engineer John Shikalsky is one of the countless inhabitants that call the city that never sleeps home.
So it's about 8.6 million people, all trying to live in the same space in New York. It's incredible because there's never a dull moment. There's always crowded streets. Everyone wants to live on the island of Manhattan.
And with nearly 3 million people commuting to this 23-square-mile island every day for work, engineers have nowhere left to build but up.
New York is synonymous with skyscrapers. We're the Woolworth Building, Chrysler Building, the Empire State Building. So as the population continues to grow, you need to come up with creative ways of how to build super talls in Manhattan.
Today, engineers are pushing the boundaries of design and technology further than ever before. This is 111 West 57th Street. With unparalleled 360-degree views of Central Park and downtown Manhattan, this record-breaking skyscraper is the thinnest building ever constructed.
Designing a building like this is a once-in-a-lifetime opportunity.
This is definitely one of the most complicated, if not the most complicated, residential build going on in the world right now.
What you don't see is all of the engineering feats that are behind the walls. You have all these different components that are tied together that are just incredible.
This gravity-defying giant marks the dawn of a new age of skyscraper.
It takes about 7.5 minutes to get all the way up. It's a pretty nice ride. Going all the way up, Tommy. Once you clear all the surrounding lower buildings, at this height, it's another planet, another world. This is the reason why we're building this. So right now we're standing higher than any of the viewing platforms in all of New York. When you're up at this elevation, you got 360-degree views of everything surrounding Manhattan. You got Central Park to the north, Statue of Liberty, the Freedom Tower. It really is just breathtaking.
111's daring construction team reach heights few have ever been to. They are the only people to have ever experienced the tower's unrivaled views over New York City.
Up here, we have ironworkers. They're bolting up, erecting the steel, which is pretty challenging up at 1,300 feet in the air, up to 1,400 feet. It's pretty intense. Every day, I'm blown away by the amount of engineering and time and planning it goes into putting this type of a building in place.
Built over the historic Steinway Concert Hall, 111 West 57th Street sits on an incredibly small plot of land. Once complete, this 84-story, 1,428-foot tall building will be one of the tallest residential towers in the city. With a width-to-height ratio of 1:24, it is the thinnest skyscraper in the world. A mix of bronze, glass, and terracotta cover the tower's enormous 1,257-foot concrete sheer walls. At the top, A 170-foot-high steel crown will make this tower the second tallest residential building in the Western Hemisphere.
What gets me out of bed in the morning is to take on the challenges of finishing this, putting this job together, and getting it to completion. So there's no rest until it's done.
But this ambitious project poses serious engineering challenges. How do you strengthen a skinny structure without giving up floor space?
The challenge is, how do we get rid of columns like this, minimize it, open up the floor space? You can't just take the columns out. There needs to be something there that supports the actual structure itself.
And how do you prevent such an incredibly thin tower from collapsing in strong winds? Cynthia Liu and her structural engineering team are experts in coming up with unconventional design solutions.
As we can see here, this is the existing Stanway building, and the next to the Stanway building is the new plot that we have to work with. From this angle, you can really see how narrow the new building is.
Before construction began, engineers had a 59-foot wide site to build on.
In order for the building to stand up tall like this, we have to engineer it in a way so the building can stay as is. As you can see, the building is slender and it doesn't have a lot of a footprint to sustain the load that's applied to the building. Most of the buildings will have the load imposed on the rock. But here, because the building is slender and it has to take the wind load, at the foundation of the building, there's a lot of uplifting load. It needs to be engineered and taken care of so the building doesn't fly away in the wind.
Without a wide base to support the tower, how can engineers brace it against the wind? To achieve the impossible, engineers will need to draw inspiration from the pioneers of the past. Cork Harbor, a vast network of busy shipping channels on the south coast of Ireland, where engineer Magda Heidekevich is searching for a relic of nautical navigation.
For hundreds of years, the beautiful Cork Harbor has been a very busy port. It was a gateway for trade and migration and a very important naval base. The waterways connecting to the city are very shallow at places and require careful navigation. Otherwise, the ships can run aground. There used to be floating lights to indicate the shallow waters of Cork Harbor. However, they would move around and can be even destroyed in stormy conditions. A more permanent structure was needed to withstand the force of the tides.
Despite being blind since the age of 22, engineer Alexander Mitchell had no problem visualizing a solution. In 1833, he patented a device that enabled him to build a structure where no one could before. This is the Spitbank Lighthouse.
It was built in 1853, 166 years ago, and it still withstands the powerful forces of the ocean.
Protruding from the water on 9 46-foot-long wrought iron stilts, this iconic beacon stands in stark contrast to traditional stone lighthouses on the shore.
What Mitchell decided to do was place 9 stilts that would be sitting on the seabed. However, that wasn't good enough to withstand the powerful lateral forces of the tide and also lateral forces of the wind. He had to extend those stilts down to the ground, but those stilts could be pulled up from the ground, so he had to anchor them down. So the very crucial part of the solution are the ingenious anchors that Mitchell came up with.
To secure the stilts 16 feet below the seabed, Mitchell relied on his own brilliant invention. Drawing inspiration from the corkscrew, he deployed crews on floating rafts to turn the supports and twist them into the ground. fastening the framework to the seafloor has locked it in place against the wildest winds and waves.
Whoa! We are now 9 meters above the seabed. It's really windy, very strong lateral wind forces and tidal forces. I can't even imagine how it could be here in a storm. The forces must be just enormous. But the structure is not going anywhere. It's very stable. The anchors holding this structure stable in such strong winds would become handy when building a tall skyscraper.
Spitbank Lighthouse has become an icon for the city of Cork, standing proud in the bay as testament to the resilience of ground anchoring.
When Mitchell designed the structure to withstand the forces of waves and wind, he made it stronger than anyone could have imagined. I doubt he thought that this structure would still be here 166 years later. Mitchell's novel solution of anchoring to the ground wasn't just meant for the sea. Today, when people want to build taller, they have to take into account strong lateral forces that the structure must withstand. What an amazing engineering solution.
In Manhattan, engineers have taken Mitchell's ground anchor concept and supersized it in order to secure New York's third largest tower to the ground. New York City is best known for its iconic skyline. But in this densely populated metropolis, engineers are running out of space to build. So they are forced to come up with an innovative solution that allows them to build not only super tall, but super skinny. At 1,428 feet high, 111 West 57th Street is the world's thinnest tower. This remarkable 84-story residential building features a 1:24 width-to-height ratio, soaring high above Billionaire's Row. But securing New York's third tallest tower to the ground is a major anchoring system challenge. So engineers have taken Alexander Mitchell's ground anchoring concept to the next level. Tasked with fastening the building in place, engineer Cynthia Liu is heading down to the lowest accessible part of the building.
In order for the building not to tip over, we have 192 rock anchors. This is the rock anchor that's used on this job, which is, as you can see, it's pretty heavy and it's hard to lift, even a small piece like this. And we have about 50 of them in this wall here. The rock anchors we have here, we use in this building, heaviest you can get on the market.
Once the foundations of the historic Steinway building are carefully excavated, an incredible 192 gigantic steel rods are drilled nearly 80 feet down into the bedrock. In this case, they're not screwed in, but instead they expand to lock into the rock. As lateral wind hits the tower, the anchors can withstand a tremendous uplifting force of 57,320 tons.
This is the design drawing that we issued for this building. You can see all the little dots representing the rock anchors. All the forces are transferred to the rock anchors in the area. The rock anchors transfer to the rock underneath. So the forces is transferred from the top all the way to the bottom.
Building on Mitchell's remarkable concept, the team has installed one of the highest concentrations of ground anchors seen on any skyscraper in the world.
Each rock anchor is about 3 inches in diameter, and they vary from 50 feet to 75 feet deep below the rock. So that's holding the building. Without the rock anchors, the building definitely would turn over in the wind load. So definitely we need the rock anchors to hold the building down.
Now that a strong foothold has been established, the super slender skyscraper can rise into the clouds. The first stage of this mega project is complete. But engineers face more impossible challenges. 60 vast apartments will each occupy at least one entire floor, as well as 6 two-story penthouses. But high winds equal high stakes. Even once secured into the rock, the superstructure is exposed to the battering elements. Protecting it from bending and breaking is the top priority for project director John Shikalski.
So down here, we're about 50 feet down below street level. And you could see that these massive columns act to take the load of the structure from the wind and transfer it down floor to floor to floor into the foundation. As you get into the superstructure where you're trying to create these luxurious apartments with grand views of all of Manhattan, you don't want a giant column like this in the middle of your living room or dining room. So you can't just take the columns out. You need something there to hold up the building.
Both floor space and rigidity are crucial in a residential high-rise. Defending the slender tower from breaking in the wind might be impossible without the innovators of the past. Chicago, the Windy City. Known for a skyline punctuated by soaring skyscrapers.
This view never gets old. It's one of the world's great skylines.
Architect and historian Tom Leslie is in search of a daring innovation amongst the city's towering giants.
Chicago is the city that really pushed the development of tall buildings further than any other city. This was a real laboratory for tall building construction. So the big development was to move away from brick construction and to replace that with steel. As buildings get taller and taller, they start to get so tall that the steel frames are too flexible. They move too much in the wind. And there's a limit to how tall you can build a steel frame. Beyond that, engineers are looking for another way to help stiffen the buildings.
To demonstrate the problem, Tom has scaled it down.
So we have here a working wind tunnel that's used to test skyscrapers to see how they respond to wind. We're going to use it to test this model of a frame. We have girders, we have beams. So we have here a curtain wall. It has no structural capability on its own. It's very much like a glass skin that you would hang on the outside of the structure. We've turned the wind on, and as you can see, it's having quite an effect on our building frame. It's deflecting quite a bit, and it's moving quite a lot. It's not a building any of us would ever want to be in. We have to find another way to help stabilize it, to make it stiffer against the lateral force of the wind. So one way we can stiffen the frame is we can take pieces of the building that we already have, elevator cores, fire stairs, things like that, and we can put a very massive, stiff core around them.
But a large core, or even columns, take up valuable floor space.
So what we've done is we've taken our giant core and we've put it right in the middle of the building structure. It's bearing on several of the beams, which in turn are sitting on the girders. So you can see that the central core is working, it's stabilizing the building, but you can also see that the frame is still moving quite a bit. The other problem with such a massive core is that it's taking up more space than we'd like. We're not able to rent out the space that's within the core.
When faced with the challenge of bracing a tower without compromising floor space, engineer Fazlur Khan conceived an ingenious way to utilize pre-existing structural components. His remarkable space-saving technique was the shear wall interaction system.
We can take the wind resistance that that massive core has and spread it out into a pair of shear walls, tall planes that line each side of the building and resist the wind. This spreads the resistance that the core has out, which will give us the open floor plates that we want.
With rigid exterior walls, the size of the inner core can be reduced. And Khan's clever addition was to connect the components with stiff structural floor plates so that the whole system worked as one.
We've turned the wind on, and as you can see, all of the pieces of the building are working together. We're taking advantage of the stiffness of the shear walls, the stiffness of the core, the stiffness of the floor plates. All of them are working together to create an integrated wind-resistant system.
And Kahn was able to prove his theory worked on a scale never seen before. This is the Brunswick Building, the world's first tower to be supported by shear wall interaction.
The Brunswick's exterior structure is 4 massive shear walls. On the inside, there's a set of shear walls within the building core. To tie these two systems together, Kahn designed very, very stiff concrete floors that ensure that when one system moves, the other system has to move as well. Kahn used things that were already there, and so the floor plates in the Brunswick building are all open between the core and the exterior wall. More than 80% of every floor is rentable, which is an incredibly high number for the era.
Braced by shear wall interaction, the Brunswick Building opened in 1965 as the tallest reinforced concrete structure in the world.
The Brunswick was a building that was miles ahead of its time when it was built, and it's a building that was influential for generations, even down to today.
At New York's sky-high megastructure, engineers are taking Kahn's pioneering technique to new heights. Just like in Chicago, they're bracing the high-rise with a shear wall interaction system on a colossal scale. .111 West 57th Street is on track to become the thinnest skyscraper in the world. But in order to endure high winds, it will need a very sturdy structure. So engineers are bracing the high-rise with a shear wall interaction system.
So here we are on the lower floors of the actual superstructure, and you can see how big the shear walls are. They're over 5 feet thick down at the base of the building. They're pretty massive. The shear walls here extend about 60 feet below street level to 1,257 feet in the air. They are some of the tallest shear walls on the planet.
The interaction system at 111 West 57th Street has 5 shear walls, all working in unison. The east and west walls form the exterior structure and flank 3 core shear walls, including the elevator shaft. As 1.3 million cubic feet of concrete is poured 1 floor at a time, the configuration rises like an oversized I-beam to over 1,247 feet high. As the mammoth shear walls climb to the highest levels of the tower, they undergo a transformation.
So here we are on one of the upper duplexes in the tower. And as we get higher up in the building, the shear walls take a step in 2 directions. They lengthwise, they shorten up, and widthwise. So you can imagine this wall was over this wide down in the subcellar, and as you got up into the building, it's about 1.5 feet thick. By having thinner walls up top, it increases the usable floor space and apartment space actually on the floor plan.
Not only do the shear walls taper in width, they also take steps in length to create the tower's feathered profile. 85 stiff concrete floors tie the system together, forming one massive monolithic structure. Should wind hit from any direction, the load is transferred through the rigid components downward into the 66-foot thick concrete foundations.
So the giant columns you saw down in the basement no longer exist up here, which opens up the entire floor space.
By pushing the limit of concrete construction, the monumental project at 111 West 57th Street can climb into the sky.
The shear walls act just so much more than regular walls. They're transferring all the forces down into the foundation. Without the shear walls, there's no way this building would have been possible. All the engineering that's gone into the design of the shear walls, being able to handle all the outside forces is just unprecedented.
With the monster shear walls topped out, the building stands proud over New York. But left untouched, a colossal concrete pillar could be an eyesore on the city skyline. Architect Dana Getman has a creative solution to make the super slender stand out.
This tower is really unique in that the east and west facades are the structure. And to really take advantage of that, we clad it with this beautiful terracotta, which we designed with a waving undulation of shapes that'll create a shadow pattern as the sun casts across the facade. When we started the design process, we really looked at the DNA of New York City buildings. We really wanted to get that richness, but in a contemporary design.
But the building's distinctive form makes facade installation extremely challenging.
It is unique to have double shear walls on the exterior of your building. Most of the time when people install a curtain wall, you slide it to the edge and you hang it from the floor above. But when you're installing it on a shear wall, it's a little bit more complicated.
With solid concrete obstructing the way, the team has come up with a one-of-a-kind installation method to navigate the unique wall configuration.
The team here on site built the custom gantry to be able to take the facade panels to their position on the shear wall.
Once hooked up to the crane, facade panels are flown out over the city, dangling hundreds of feet above the street. The enormous pieces are traversed around the outside of the shear walls to the installation team on the gigantic two-stage hanging gantry. They have to change hands several times in a precise and delicate procedure to fix them to the east and west shear walls. The result is a striking hybrid of New York's Art Deco heritage with the cutting-edge architecture of the future.
I am incredibly impressed with the team here on site and how smoothly the installation has gone. When you look at the building from a distance, you see the waves of shadow and you really see the impact of this building on the skyline. We couldn't be happier with it.
But to realize their dreams of creating extraordinary apartments, engineers face yet another challenge.
So our units are 15'6" from floor to floor, and that creates the need for larger pieces of glass in order to maximize the views that we have.
To create more impossible engineering, the team will have to go back in time.
Oh wow, I can see the ripples it's made.
That's what glass stuff.
So that's the glass floating on the tin.
Soaring over New York's prestigious Billionaires Row is the city's latest mega project. 111 West 57th Street is the world's thinnest skyscraper. Rising into the sky, it towers above the neighbors and the city below. Construction of the third tallest tower in New York is nearing completion. The project's final phase is underway, preparing 60 luxury apartments for habitation.
All right, you going all the way up?
Yeah.
When you're done, we got to pick up on one.
But to make the whole development worthwhile, Senior Project Manager Pat Feehan and his team have one last challenge to conquer.
So right now we're in a hoist, which runs the north side of the building. You know, looking north from east to west, we're dead center looking over Central Park. It's a pretty incredible spot. The units that we have in this building are going to be the only units on 57th Street that are going to have a dead center view over Central Park.
Pat's team must take advantage of the tower's unrivaled views of the city. Not an easy mission to accomplish in such enormous living spaces.
So our units are 15'6" from floor to floor. That creates the need for larger pieces of glass in order to maximize the views that we have. We need to find a solution to make sure that we can see them perfectly from the units.
To find vast window panes worthy of the unprecedented panoramic views, the team must look to the pioneers of the past. St. Helens in the north of England. Legendary for industrial innovation, where physicist Susie Sheehy is heading underground in search of a development that shook the world of glass production.
These tunnels are actually below a glass smelting furnace, and all around here there would have been coal fires that would have been so hot for the workers working down here. What they were aiming for was to make large panes of glass for windows that were clear and strong and free of blemishes. So they'd take molten glass and pour it over a metal tray where it would cool down. But the result was something that was imperfect. It was blemished and rough. So then they'd have to grind and polish it. Even then, the panes they made were not super big. It was only up to a couple of meters. So to get something even bigger and better, they'd actually have to come up with a totally new solution.
But for Sir Alastair Pilkington, the answer was crystal clear. In the 1950s, he developed a revolutionary new process.
So this place is the solution that Pilkington came up with, and it's absolutely incredible. I've just seen in front of me here this huge, really flat sheet of glass. Absolutely beautiful.
Pilkington's float glass innovation quite literally broke the mold.
It's so flat because they pour molten glass onto a bath of molten tin. And that's so flat that it comes out in these enormous sheets. They're just incredible.
This cutting-edge plant has modernized its machinery, but remains true to Pilkington's technique.
Oh, wow. I can feel the heat radiating off this.
For any glass production process, a sand-based mixture must first be melted to a scorching 2,912 degrees Fahrenheit. But what sets this extraordinary method apart is what happens next.
Woo! Nice.
In the 1950s, Sir Alastair Pilkington invented the float glass process, a revolutionary method to manipulate the size and thickness of glass. After a sand-based mixture is melted at nearly 3,000 degrees, it is fed into a molten tin bath chamber.
So this is about 25 kgs this, so it's quite heavy. We just step to the side and place it into the box.
That's amazing. And then I get to
Yeah, if you just stand back.
Yep.
Just push it gently in. That's it. Brilliant.
Will that do? All right.
Just leave it there, and you'll see it melting away now.
Oh, wow. I can see the ripples it's made.
That's the tin.
So that's the actual bath of melted
That's the actual tin. That's what the glass is floating under.
Wow.
So if you look at it straight up there now,
Yep.
that line that you can see, that's the actual glass there.
So that's the glass floating
That's the glass
on the tin.
floating on the tin.
It just looks like a mirror.
Does, yeah?
Yeah.
As a liquid, molten tin sits perfectly flat. Glass from the furnace is slowly poured over the lake of metal, and being less dense than the tin, it floats atop the surface, spreading and cooling in a flawlessly smooth sheet. The glass leaves the bath with so few impurities that it's crystal clear and incredibly strong, properties that would make for great skyscraper windows.
So this section is where the solid glass comes out, and it's really beautiful and flat and clear, perfect for windows. But when they first started using this float method, they had glass that was just 6 meters long. But now they've perfected it to the point where they can just get a constant, unbroken flow of glass over this 600-meter length. And this one here, it works 24 hours, 7 days a week, and hasn't switched off for more than 7 years. It's so reliable. It's just an unbelievable method.
The float line can run continuously for 20 years, producing around 479 million feet of glass, enough to wrap around the Earth 3,500 times.
So as it comes out here, I can't see a single imperfection in these panes. This method just produces perfect glass. And that's only possible because of this float glass method.
"70 years after Pilkington's inspired idea, New York's greatest engineering minds are using float glass to provide views unlike any other on Earth. Pat Feehan is overseeing the installation of 111's supersized insulated glass units.
So on the exterior facade, this is the exterior facade of the glass. So there's 3 individual pieces of float glass made up into these glazed units. They have 2 pieces of laminated glass on the exterior facade, and then 1 piece of a slightly larger, thicker glass on the interior facade with a 12-millimeter argon gap. The technology that goes into the glass in particular allow us to make the panels that we can make today. And if it wasn't for the float glass, we wouldn't be able to make panels like this.
The tower's massive glass panels owe their immense strength and clarity to the float glass method.
So the actual essence of the glass itself is pretty fundamental, but the technology that's come around along it that have allowed us to get larger panes of glass, stronger glass, allow us to push the material as far as we can go.
Although each apartment has solid east and west shear walls, they're completely open to the north and south. The team's task is to fill a void over 59 feet wide and nearly 16 feet high on each floor, with huge panels of crystal clear glass to minimize view-obstructing joints. The largest panel, which will form the centerpiece of each apartment, weighs over 1 ton, as much as a small car. Installing these massive window panes at extreme heights is an intense operation. And the team will have to carefully pull off a daring act of engineering. In New York City, engineers are preparing to install massive glass window panes on a groundbreaking new residential skyscraper.
So right now we're getting ready to install this panel, so we're gonna be flying it out from this floor. The tower crane's gonna come down with the hook, we're gonna hook it up, and we're gonna send that panel out and install it onto 69. It's not a typical install, because the panel is so large, gets caught in the wind, it could blow around. Everyone has to be, on their game a little bit more. To be doing this work, you have to be able to deal with the height and be able to deal with working on the slab edge, which is not an easy thing to do.
Just hold on to that, Philly.
The fearless installation team pushes extreme construction to the very edge. The oversized, heavyweight panel is lowered 5 floors down. One wrong move could spell catastrophe.
We're going down to level 69 where this panel's gonna get installed.
With the success of the installation hanging in the balance, the team need to work quickly to secure the panel into the interlocking weather seal.
Hold that.
So, we have one panel now installed of over 6,500 total on the building. Installing panels one at a time, it doesn't feel like you're getting anywhere, but after a while, they start to add up. We're on the 69th floor right now installing panels. We're approaching the end, which is kind of incredible. There's a lot of amazing things about 111 West 57th Street, but I think one of the key things and one of the biggest selling points is the view that we have here. The technology that has gone into making glass has progressed so much over time that it allows us to make panels the size that we have here, to have them as clear as they are, to have the views that we have. We have the whole entire skyline to look at. It's kind of incredible.
For the team behind this daring project, the engineering achievement is immeasurable.
Looking at a postcard 20 years from now with the skyline of Manhattan, it's going to be a building that I built on there. It's kind of incredible.
Every day we look at the building, see it grow. It's really incredible, and we feel like very lucky to be part of the team to work on this.
No matter which aspect you look at this building, it has definitely enhanced New York City skyline. It's taken pieces of old New York and new New York and combined them together and created something that the world has never seen before.
The super slender skyscraper that has defied the impossible, pushing the limits on tower construction further than ever before. A new landmark vanishing into the clouds, changing New York's skyline forever. Standing testament to the incredible work of some of New York's greatest engineering minds. .111 West 57th Street represents impossible engineering on a staggering scale. Every stage of this groundbreaking enterprise poses unimaginable challenges.
When we first started this project, I knew we were doing something special. This is one of the most unique superstructures that you could ever put together.
But by building on the work of the pioneers of the past, overcoming huge challenges, and pushing the boundaries of innovation.
I'm incredibly proud to be working on this project. It's incredible, and it's more than I could have asked for.
We really saw it as an opportunity to do something that both spoke to the past, but also looked to the future, and to see it not just through design, but now almost complete and physically here is really an incredible experience.
The engineers are succeeding in making the impossible possible.